Okay, to finish up our review that we started today in class, this is the question that we were looking at, and we didn't get a chance to do this one. Um, I'll read the question, and the operative word is has a relative max at x equals 3. There's a process for relative maxes. That would be find crit points, endpoints, intervals, and then you determine if it's a max or a min. So let's begin that process. I'm really not sure why, but let's go ahead and do that. So I need to take the derivative of this function. Oh, I don't like the way that looks. Let's write that as 2dx plus 9d x to the negative 1. Okay, now I'm ready. So its derivative would be 2d. Bring the negative 1 in front, so negative 9d x to the negative 2. And again, let's straighten it out. That's 2d minus 9d over x squared. And to make that a critical point, I'm going to set that equal to 0. Now I'm thinking, well, I got a fraction there, so I could get a common denominator. But wait a minute. If I have a max at x equals negative 3, that means there's got to be a critical point there, which means all I have to do is plug in the x right there, because maxes and mins occur at endpoints or crit points. And they're telling me that x has to be 3 because there's a max there. So let's plug it in. And look what we get. This is so nice. We get 2d minus 1d equals 0. So 1d has to equal 0. D has to equal 0. And G, that's what I'm looking for. Did I answer the question? I found the value of D. Okay, this next one, we'll start with a graph. And we'll start with the graph being a derivative. Now I can ask you a series of questions based on this graph. So I'm going to stream through a series of questions. First question I could ask you is, where are critical values or crit points? Well, by definition, that's where the derivative is equal to 0. And if they're giving me the derivative picture, I just look for the zeros. Easy enough. At negative 7, negative 2, and 5. Now another question they can ask you is intervals of increase or decrease. So just like we always do, you want to break up your universe into these intervals. So negative infinity, negative 7, negative 7, negative 2, negative 2, 5, 5, infinity. Now I need to pick a number between negative infinity and negative 7, so I do that. And I pick a number, and it's somewhere down here. That's definitely a negative number. Pick a number between negative 7 and negative 2. That's clearly positive. I pick a number between negative 2 and 5, positive, because these are the derivatives. And then any number above 5, I would get a negative number. So that means it's got to be decreasing here, increasing here, increasing here, and decreasing. Now, keep in mind, I could say, hey, is it increasing from negative 5 to negative 1? Is it increasing from negative 5 to negative 1? The answer is yes, because that falls inside this interval. So don't be thrown off because the interval doesn't match up with what we have here. I can also say, like, the function is decreasing. Is the function decreasing from 6 to infinity? Well, yeah, that fits in here. Okay, now, obviously you know what the next question would be. Next question would be what? Are there any maxes and mins? Any extremes? We were following our steps already. We did crib points, we did intervals of increase, decrease, which gives us an image of what the function looks like. The image of the function is it has to go down to -7, come up to -2, level off, go up to 5, and then back down after 5, leaving me with a max, or a min, sorry, min at x equals -7, and that means I have a max at x equals 5. These guys do not indicate there are any bounds. So this guy down here over here and this guy to the left can't be considered extremes. Okay, now I'm going to go back up to this picture and ask another question. Let me erase these things. And we're still going to consider this function to be the derivative. Now, other questions. When is the function concave up or down? Huh. Well, if I ask that question, then I should be thinking about the double derivative. And if I'm thinking the double derivative, then if I'm looking at the derivative, I'm thinking of the slope of the derivative. So, if I have a slope on this graph that's positive, then I know it's increasing. So on this interval from here to roughly right about there, let's call that negative 5.5. It's concave up. Then I go in this interval here from negative 5.5 to -2. It's clearly going down, which means my slope of my derivative or my double derivative is concave down. Then I've got another section here from -2 to 3. That's included an increase part of the function, which means the slope of the derivative is positive, which means the double derivative is positive. So I'm going to add from -1 to 3 to my concave H section. And then it's concave down because the slope is down here. So union 3 to wherever. Final question. Same picture. Points of inflection. Well, virtually we have the question answered, but remember, the definition of point of inflection is the concavity must change, which means the slope has to change. Positive, negative. So at this location, I have myself a point of inflection. Where else? Well, it also changes from here to here. It went from negative slope to a positive slope. So I've got another point of inflection at -2. Then from 3 up to 3, then down to 3, from 3. So therefore, 3 is also a point of inflection. Warning for you. I'm going to erase all this. I'm going to ask you the same question, but I'm going to provide you with different information. What if, instead of giving you the graph of the function, I say this is the double derivative graph? Now I'm going to ask for points of inflection. And remember, this is now the double derivative. So I'm still looking for where the concavity changes. So first, let's find where the derivative is 0. That occurs here, here, and here. If this graph is my double derivative, then my double derivative here is negative. Here, my double derivative is positive. Again, here, my derivative is positive. Then from 5 over, my double derivative is negative, which means that here I got a negative to a positive. It changed. So that gives me 1 point of inflection at x equals negative 7. Here, it goes from positive to positive. No change, no point of inflection. Not. And over here at 5, we got a positive number, a negative number. It's changed from positive concavity to a negative concavity, so it is a point of inflection at 5. Okay, so that's pretty much the graphing kind of things we can be asked. So let's move on to the next page. All right, linearization. We haven't done that in a while. Remember, linearization is equation of tan line. That's what that is. The difference is we're going to use it to approximate. Okay, so I'm going to write the equation of a tangent line because it says linearize. Write the equation of a line. So I'm going to find my slope by taking the derivative of f, which is going to give me, if I put the 4 in front, that gives me just x cubed. Now again, remember, there's that stupid fraction thing again. That subtract 2x to the negative 1, giving me plus 2 over x squared. Okay, there's my derivative. Now I need to know where I want this slope. I want the slope to be at x equals 2. So my slope is 2 cubed plus 2 over 2 squared, which equals 8 plus 1/2, which is 17 halves. Okay, so I have my slope, I have my x, I need y. Of course, we go to the original to get that. So 2 to the 4th over 4 minus 2 over 2 is 16 over 4 minus 1, which is 3. So now I've got all my components. Let's put together my equation, my line. My line is now used as a linearization, so L, slope, x minus x plus y. Okay, now we have our linearization. Now let's answer the rest of the questions. I'm going to use it to approximate f2.1. So f2.1 is approximately equal to the linearization at 2.1. And that linearization is equal to 7 over 2, 2.1 minus 2 plus 3. The beauty of this is we can actually do this by hand. It's not always, glorious like this because we've got all these fractions, but 2.1 subtract 2 is 0.1 or 1/10. So I'm going to write 1/10 plus 3, which means my function approximation in decimal form is approximately, that comes out to 3 17/20. Now, we've approximated. The question then is, how good is my approximation? Is it too high or too low? Remember, if it's concave up, the line is above, my approximation is too high. If it's concave down, my line's below, then my approximation is too low. So concave down, it's too high. Concave up, it's too low. Okay, so that's what we're looking for. So let's look at we need concavity, double derivative. So I just got rid of my derivative. So let's rewrite that derivative real quick. The derivative equals x to the 3rd plus 2 over x squared. So let's take the derivative again. Oops, better write it in a better form. There we go. F double tick x equals 3x squared minus 4 over x cubed. All right, now we're checking to see what the concavity is, where we drew our tangent line. We've got a curve, we want to know where that tangent point is, because that's going to tell me if I'm bowing up or bowing down. So plug in 2, and you can do the work here. That's going to be 12 minus 4 over 2 cubed, which is 8. That's clearly a positive number. Since double derivative is positive, it tells me the curve is concave up. Therefore, my L 2.1 is 2, oh, I don't know, I can't remember. Let's see, concave up, too low, too low. Okay? That's mastering linearization for you guys. That's all we need to know how to do. All right, hey, another point of inflection question. Which means I'm looking for the double delish, and I gotta make sure the concavity changes. They give me the double derivative. Whee! Okay, so let's set that double derivative equal to 0. Well, if I do that, I gotta set this equal to 0. I gotta set this equal to 0. I gotta set the final factor equal to 0. So x is 0. X is negative a. And you could cube root or fourth root that guy, that 0, that gives me nothing. Then add b, gives me b. So those are potential points of inflection, but I got to make sure they changed. So let's check the intervals on each side. It's the only way I'm going to know if I have a point of inflection at these values. Not sure where a and b are. Not really going to be relevant, because what I'm really doing is checking each side of the 0. So if I check on each side of the 0, I pick a number over here. Wait a minute. This is always positive. That's always positive. So it's really not going to matter on which side I am. So what I'm going to do is I'm going to say, okay, on each side of the 0, that's not, this value is not changing. Okay, it's always positive. That's always positive. So here, I'm getting a negative. But right next to it, I'm also getting the same value. I have to, because it didn't change. In other words, whenever I see the root comes from an even power, I know I'm not going to get change. Now, a is an odd power right there. That's an odd power. See? Power of 1. Odd. That means these two got to change. Even if I can't figure out what the values are, I know they've got to change because that's an odd power. Here, even power. So on the b, at b, I know this cannot change because that's an even power. So that means I have exactly 1 point of inflection at negative a. Done. So be cautious when they give you the double derivative. You're looking for those even powers, because those roots of this double derivative function will give you no point of inflection. It's only when there's an odd power. Otherwise, we got to actually plug in values to find the roots. Now here's an all-encompassing question. Find the extremes for the intervals decrease, which individually they could be questions. But the processes pretty much remain the same. Extremes, intervals increase pretty much fall in the same category. You still need those crits. So derivative set equals 0. X squared equals 3. X equals plus or minus the square root of 3. So I got my crits. Second thing, ends. Don't have any. Step 3, intervals. It's really kind of tough without seeing you guys. It's kind of depressing, but okay, I'll just keep dealing with it. All right, let's check the value of my derivative. My derivative is here. pick a number like negative 100. Negative 100 squared is a big old number times 3, subtract 9 is clearly positive. In this area here, I'm going to pick 0. 0 subtract 9 is a negative number. And then to pick a real large number like 100, that's a big number, subtract 9 is positive. That tells me I have an interval of increase, interval of decrease, and another interval of increase. So I've answered one of the questions. Now to go even further, I now can tell you where my extremes are. The curve goes up to x is radical 3, negative 3, down to radical 3, and then back up and out the door. That gives me a max at x equals negative radical 3 and a min at x equals radical 3. Now, if I ask you what is the max, if I ask you what the max is, this is not what the max is, that's where it's at, which means I've got to take this guy and find the value, which means I got to plug it in here. Don't worry about that. That's going to be an ugly solution. You would probably want your calculator there. Now, if I want the min, again, this is where it's at. To find what my minimum is, I would plug it in here. And in the event, if I had two minimums, I'm going to check both of those y values and see which one's the lowest to determine the absolute max or absolute min here. All right, it leaves me one more question, and that two more questions. The concavity and points of inflection both stem from your double Delitzsch. My double is 6x. Can't make it much easier than that. Now we're going to set that equal to 0. And when I set that equal to 0, I get x is 0. Now I'm going to check the concavities because I need points of inflection, need to have a change in the concavity. So let's see. Since I'm checking the double derivative, that means I'm looking at my double derivative. Pick a number like negative 5. That's negative. Plug in 3. You get a positive. That tells me this is concave down. From 0 to infinity, it's concave up, which implies because these two change, it means that I have a point of inflection in that area. Okay, that concludes the final of the review. I will be in the morning to do any additional questions that you may have. You have review questions to work on. The test is 2 days. We'll do the shorter part, then first day I see you. So on Thursday, we'll take the shorter part of the assessment then.